Greetings and welcome, internet friends. Mr. Waddy is here hanging out at home. I've got Legos in plain sight. This is great. Got my Xbox 360 gaming headset on and trying the remote teaching thing for a little bit. So this is going to be interesting, but we'll try it out. And so today we're taking a look at Algebra 2 textbooks, Chapter 2, Section 4, Characteristics of Quadratic Functions. And we're taking a look at the exploration for starters, and we're going to do this one together. And so this is about a wrench that has been dropped, and it's being dropped a number of feet. Looks like 400 feet at time 0, and it falls over t seconds. And so it says use a graphing calculator. We're going to use Desmos here in order to accomplish this, to create a scatter plot of the data. Already done. And oh, it's already shown. Boom, good. And so this data could have easily been collected right in the real world, and then you model that over time, and I anticipate that we're going to get some sort of quadratic, right? If I could hit those points, it would look something like that. But I'm going to use the graphing calculator's quadratic regression feature. And so you might remember best fit lines from back in the day, right? Y equals mx plus b given a scatter plot in which you would possibly draw those by hand. And we also had whether you use graphing calculators, Desmos, GeoGebra, whatever the case may be, spreadsheets even, you could predict the best equation that models that. And so here we are, we've got our points, and I'm going to use Desmos to calculate that best equation. And so I've already got this lined up, and if you've got the notes, you can actually use this exact same file. And so we've got time as the x-axis, height as the y-axis, and this data appears to be parabolic, a quadratic. I think so. And so as far as using the regression feature on Desmos, it's actually quite simple. All I have to do is, instead of using y's and x's, I'm going to use y1 and x1. And I literally just typed y and then the number 1, and it automatically made it into a little tiny subscript. And if I hit the tilde key instead of the equals key, tilde is shift, and I don't know what that other button is, but it's next to the 1 button on your keyboard. And so let's say I was doing y equals mx plus b. So I could actually do y is approximately m parentheses x1 plus b, and it'll give me a line that represents that equation, all right, or represents that data set. And it doesn't do a great job, right? It's missing most of them, and you can tell that it's kind of curving. And so you actually literally can write the equation of a line. And so in our case, I suppose we have a few different equations we could write, because we have standard form, vertex form, intercepts form. Let's go with standard form. So I'm going to do y sub 1 is approximately, by the way, is what that tilde sign means, a parenthesis, or a x1 shift 6 gives me the caret, gives me the access to the exponent here, x1 squared plus, and now I'm gonna keep typing it out, and everywhere there was an x, I'm gonna type an x1, and then plus c, and boom! Look at that! Woo! It actually hits that pretty accurately, and I now have an equation that models that. Well, I've got a graph. Where's the equation? Well, I've got the approximate values of a, b, and c right here. And actually b, what is going on with this? That's right, you can guess that 10 to the negative 15th power, it's approximating this to be 0 is what's taking place. And so if I wanted to model that the same way, I could actually just type y equals negative 16x squared plus 400, and you can see that pretty much gives me the same thing, because that is 0.0000, right? A total of 14 zeros before it hits that number 1. And so here's my equation. So let's write that down. Y equals negative 16x squared. Or actually, you know what? Let me invert colors and screenshot, and I'm gonna yoink, steal that right there. Beep beep beep. And oh, that's not gonna line up, but that's okay. I'll just plop it right there. And so the equation of our line is y equals negative 16x squared. Oh, I guess I should technically use h's and t's. I'll do it. H equals negative 16t squared plus 400. And right, we're familiar with that. Oh, because there is no b term, 400 is the y-intercept and the vertex and all of that. So let's see, graph the quadratic function on the same screen. Did it. Cha-ching. And then question, when does the wrench hit the ground? And so that's a question regarding an x-intercept. So yeah, I've already got my vertex up here. And if I want to calculate the x-intercept, you can see I could probably estimate it based on what I have. I technically could calculate it by plugging in 0 for h and solving, but we haven't done our solving unit yet, oddly enough. But let me show you how easy Desmos makes it. I literally just click, oh, boom, right like that, and 5, 0 is the point. And so it will automatically give me the intersection between those two. And so what does 5, 0 mean? Well, it meant that time was equal to 5 when h was equal to 0, right? That's 5 seconds and 0 feet. And so it occurs when the graph crosses the x-axis. And so there we go. So I'm able to model real-world data. I'm presently working on a Desmos activity in which you might be able to use some, oh, I'll tell you what, spoilers behind the scene. I'm working on this, where you'll actually be able to try to model some equations based off of some sequence shots. And so here's some cool dude jumping over a ravine, canyon sort of thing. And I'll have you guys do some of that calculation later. But there you go. Ooh. Little preview of what's taken place. So there's our exploration. But let's jump into this. So if I was not to use a graphing calculator, there are ways to calculate these things without. And so we've currently got 3 different forms. So this was standard form, which, by the way, is not the greatest form for quadratics, because it's the only thing it's good at. Well, let's give it credit. It's good at giving you the y-intercept, right? 0, Charlie is the y-intercept. It's good at that, and nothing else, because you have to actually like do this whole little equation, negative b over 2a, in order to calculate the x-coordinate of the vertex and then plug it in, etc., etc. So standard form, not the recommended form if I have some points. But vertex form, that is a great form to work with, because A, there we go. A would help me determine which way it opens, and the slopes, right? We knew that, and H and K represented the vertex, right? H, K. And now the third form that we ended up learning was intercepts form, in which A is the same thing. Where's my A at? All right, A is the same thing, but P and Q represent the x-intercepts. So that means there's a point P, 0 and Q, 0 on the graph. And so intercepts are pretty important. They're not as important as the vertex, but that's going to help us out. Now, there is a way to find the equation of a parabola if I give you, so these are recommended routes that if I gave you a point and a vertex, vertex form is a great choice. If I give you a point and an x-intercept, or both of them, actually, yeah, you would need both of them in this case. Unless you had a vertex, but that kind of already was indicated right there. And so if I know the intercepts and a point, this is the preferred method. And there is a way to do it using 3 points in which none of the points were necessarily intercepts and none of the points were the vertex. And that requires solving a system of 3 equations and 3 variables. And so we are going to do that. Man, my writing tablet has been wonky lately. We're going to do that later, like later on in this course, whenever we do a system of equations unit. systems of 3 will figure that out. And in that case, that's when I probably would use standard form. And that's going to be the easiest way to work. And so here we go. Let's take a look at example 1. The graph shows a parabolic path of a performer who is shot out of a cannon, where y is the height in feet and x is the horizontal distance traveled. So the x-axis does not represent time. This is a path equation that's being modeled, not a vertical location given time sort of thing. Write an equation of the parabola. And so what do I currently know? Well, oh, wow. We actually know the y-intercept right here. So that's kind of nice, although I didn't even need it, even if I knew a different point. But I suppose if I was gathering data, I would know the height of the cannon, right, that the person is being fired from, 15 feet. That's an easy thing to measure. And then as far as this is the vertex. And did they tell us? No. They didn't specify that, but that's definitely the vertex. And so this is going to be my h and my k. And so h equals 50, k equals 35, and I have a particular point. I'll call it x1 equals 0 and y1 equals 15. So that's a particular ordered pair that makes the equation true. And the form of the parabola equation that I'm using, the fact that this was the y-intercept isn't actually going to help me all that much, but that's okay. So since I knew the vertex, I'm going to use vertex form. And so vertex form is y equals a parentheses abs x minus, nope, I just said abs. I was thinking of the absolute value graphs. It's quite similar. X minus h quantity squared plus k. And so notice right now I know a handful of these things, and I'm going to plug in what I know and solve for what I don't. And so I know y is 15, or I know ay, sorry, is 15. I know a particular x value is 0. I know the h and k, and so I'm going to write minus 50 here and plus 35. And I'm plugging in what I know, and I'm going to solve for what I don't know. And the thing I don't yet know is this a value, right? That's what I'm looking for. And it's, if I know a, then I could know, right, a, h, and k. I could write the equation and then make predictions, which is what they want us to ask, right? The performer lands in a net 90 feet away. So we're trying to figure out how high is that net. And that would be helpful to know prior to launching the performer, unless you just have a large enough net, right? We don't want them to. I mean, how many performers did we have to shoot out a cannon before we knew where to put the net, right? This is where math is helpful. And so let's figure this out. So 15 equals a times negative 50 squared plus 30 I wanted to say nueve, but I was looking for a calculator. Cinco. Boom. There we go. All right, there we go. So let's see. I'm grabbing my little calculator here at home. It's actually one of my kids. They got it for their birthday. It's pretty great. Oh, dear. 50 squared. 15 equals a times 2,500 plus 35. And so I'm just solving for a, old school algebra style here. So I'm going to subtract 35 from both sides. I'll get negative 20 equals a. Or tell you what, let's write it as 2,500a. And to get rid of that a, it's currently being or the 2,500, it's currently being multiplied by a. So div both sides by 2,500. And so I'm going to get my a. It's going to be negative. And I'm getting 0.008, which I believe, if I did this, is the same as negative 1 over 125. But we can work with the decimals in this case because typically that's what we're going to have. And so now that I have my a, h, and k, I've got the most important parts of my equation, and so I can write my equation. Y equals negative 0.008 times parentheses x minus 50 squared plus 35. And so this time I don't plug in the x and the h, or I guess I could have said, what was it? I already forget what variables they were saying. Oh, no, they did use x and y. Excellent. And so I leave the x and y generic, so it represents all possible points that make that equation true, which are all of these points, right? All of them. And so now the final question is, the performer lands in the net 90 feet from the cannon. And so I know that the x coordinate is 90, and I'm looking for the y coordinate. So I'm just going to use this equation, plug in 90. So negative 0.008. Let's make a better decimal there. I'm plugging in 90. And I'm just going to now PEMDAS this, just evaluate it. Negative 0.08 times 90 minus 50, I believe, is 40. Meh. And, forgot my square. So 40 squared. I'm doing the exponent before I do the multiplication, mind you. So that's 1600. Multiply that by 0.008, and I get negative 12.8. Make sure you're following along at home. Plus 35. And final answer, 22.2. And so what does that represent? The net is 22.2 feet high. And so this is the value of quadratics and parabolas, is that not only can you write an equation, but now you can make predictions using that equation. And so, yeah, we're able to figure that out. We could even make calculations like how high would hoops have to be that are lit on fire that, they'd have to fly through. And we'd be able to figure that out. Like if I plugged in 20 for x, I'd know exactly how high that hoop had to be. If I plugged in 75 for x, I'd know exactly how high that hoop had to be. And I could figure out all sorts of things. And so because one of my points was the vertex, that's why I chose vertex form. All right, if I'm given a point and the vertex, that's the easiest way to take. And I bet you can guess what's next. We're going to do one of these kind. That's right. All right, let's pick up the pace, Mr. Waute. I'm going to grab a sip of water. You guys flip the page. Go to example 2. All right, well, we're looking at temperature prediction. All right, here we go. Speed it up, Waddy. So this time I know, I know 2 of my intercepts, right? And so P is equal to 4, Q is equal to 24, and then I know a particular ordered pair. It happen to be the y-intercept again. So I'll call this x1 equals 0, y1 equals 9.6. And so what is my general, or I don't want to say general form because we use that terminology elsewhere in mathematics, intercepts form. So y equals a parentheses x minus p times x minus q, where p and q are my x-intercepts. And so per usual, I'm just going to plug in what I know. So 9.6 is a particular y value that makes that equation true. I don't yet know what a is. X is 0 in both of these cases. And P and Q are minus 4 and minus 24. And so notice I plugged in what I know, and I'm going to solve for what I don't. I'm looking for A. And then once I have A, I've got A, P, and Q, and I would be able to write my equation and make predictions. So here we go. 9.6 equals A times 0 minus 4 is negative 4. 0 minus 24 is negative 24. and that's equal to positive 96a. And to solve, it looks like I just divide both sides by 96. Now I'm tempted to say this is going to be what, 1/10? Am I doing that right? But guys, this is the internet, and Waddy Math makes mistakes sometimes. It's too high stakes. It is 0.1. There we go. So I can now write the equation that's going to represent this. And so I'm going to write without the x and the y. So I'll have y equals 0.1 times x minus 4 times x minus 24. And so that's my equation in intercepts form. But what are they asking me for? They said write a function that models... Done. We did it. What is the coldest temperature? Now, when I hear the word coldest or hottest or whatever, I'm thinking that's a minimum. And minimum means vertex. And so we've got to figure out the vertex here. Oh, actually, there's a few different ways we could do this. I could technically foil or double distribute this out, get it into standard form, right, all the way up here. I could write it in standard form and then do negative b over 2a and then plug that in for my equation. But we actually had a different way of doing that. Since I know p and q, and the vertex is going to be literally in the middle of those, the x-coordinate of the vertex, my equation should be the average of those two things. So I would just do p plus q divided by root to 2. And so let's plug those in. 4 plus 24 over 2. And so I get, oh, I just swapped over to using Vx instead of H. Crazy, crazy, Mr. Waddy. Got to have consistent messaging here. So H is equal to 28 tooths, which is the same as, let's see, H equals 14. Now, that is not the minimum temperature. That's the hour after midnight that temperature occurs at. And so if that's my vertex's x-coordinate, to find the y-coordinate, I'm just going to plug that in for my x's. Man, I'm having a hard time with those dots today. So 14 minus 4 times 14 minus 24. And so y, I guess I don't have to write that. 0.1 times 10. Ooh, those are going to cancel out nicely. And 14 minus 24 is negative 10. And so if I multiply all this out, is it negative 10 degrees? Oh, no, they didn't. That's actually what it looks like on the graph, too. And so the output, when the input was that, the other way I could say that this is k, the y-coordinate of the vertex. So the minimum temperature is negative 10, and this is in Celsius, right? Degrees Celsius. I just spelled this wrong, but I was actually more scared about how I'm writing behind that. Oh dear. That means I'm going to have to change my layers. Celsius. Boom. All right. Fortunately, I can do that quite quickly. All right. Not to worry. Okay, I'm skipping example 3, and we're going to jump right into example 4. And actually, you've already seen how to do this one. Kind of. Says write a function that models the data, use the model to approximate the optimal driving speed. And so this one is actually another Desmos activity. Boom, I've got it right here. Look at that. And so what am I going to do? I'm going to do y1 tilde, and actually I wonder, would it let me do ah and k? Let's try it. It theoretically would. So a parentheses x1 minus h squared plus k. And look at that, it still will work. And so I actually could have written this in any form that I wanted. Actually, let's do it this way. A times x1, nope, squared plus bx1 plus c. Sorry that it gets jittery when I do that. And notice that I actually get exactly the same curve, but I find different variables for it. So here I've got AHK, and there I've got A, B, and C. Quite the thing of a beauty, if you ask me. Tell you what, I'm gonna screenshot this like so. And so theoretically, I could have even used. Actually, we should. Let's do it. We're here. Let's see if I could find the best fit equation using intercepts form. Y1 is approximately a parentheses x minus p, nope, times x minus q. What am I missing, guys? It's yelling at me. It's like, what's x? You can't use it. They need to be x1s. And look at that. It works, guys. It works. All right. Well, didn't quite line up, but that's fine. Boom, and that one's selected. Whatever. And so there we go. We find a model that represents the optimal driving speed for fuel efficiency, which, by the way, actually, I remember a Car Talk episode in which they asked, what is the most fuel efficient speed for your vehicle? Their answer? 0 miles per hour. You're not using any fuel. But I suppose you're not getting any miles either, so then you're kind of doing divided, well, whatever. But anyways, you're not using any fuel when your car is parked. And so let's see, what is the optimal driving speed? Optimal, that sounds a little bit like maximum. All right, let's see if I can write a better M there. Maximum, which means I'm thinking vertex. And so whichever form I had, here I would have found, negative b, or sorry, here I would have used the negative b over 2a method. Here I just need to figure out what k is. And boom, so the optimal driving... Nope. No. The y coordinate was what? That's the number of miles per gallon. So 20... Is that a 5? It doesn't matter. It's a 5, isn't it? 25 miles per gallon, but it occurs at h. So I wanted h for the miles per hour, because they were asking about speed, which is in miles per hour. And so h is 48.4 miles per hour. That will round correctly. 48.5 miles per hour is the optimal speed. Boom. No es más mal. There we go. And so we can make all sorts of cool predictions using parabolas. It's a pretty great thing. Not everything in the real world is linear, right? Some things have all sorts of different shapes. Okay, and that's everything I had. And so I'm going to be publishing the Desmos activity shortly. Hopefully you guys can do some sick jumps and calculate some things like that. And yeah, homework's online, all that. And yeah, let me know if you have any questions. Post them in the Google Classroom. Post them in comments below. Have a great day, everybody. Adios. Wadios.